joining us today. Um, this is the first of our lectures on, um, we call it the Winter Lecture Series. It'll cover a range of topics. Among these topics will be looking at what machine learning is good for today. We've got one on how to use quantum computing in credit risk, one on unintended bias, and one on how to use machine learning for long-range forecasting, which is also a challenge. So I'll touch on some of those today, but I want to focus more on kind of the big picture. Where should we use machine learning today, and where is there possibly more hype than reality? Of course, we all know that some of that is happening. It seems like every product you buy these days says it's based on AI. We know that that's being used very loosely in those types of things. But this series of webinars is being sponsored jointly by MRMA and by Deep Future Analytics. Model Risk Managers International Association was founded in 2018, and it's done very well since then. I'm quite proud of how this is going. I'm fortunate to have been asked to be president a couple of years back. And it's an industry organization to promote best practices in how to say this, for those who work at lenders, for auditors, for regulators. So one of the main things we do is to create work groups to explore different topics and look at what kind of recommendations they can propose. And you will find on Amazon the first volume of our journal, MRMA Best Practices. And this is a collection of the articles that were created for our conference back in February of this year. So we expect to have another conference early next year. We have work groups who are exploring some interesting topics, so we look forward to presenting that. My paycheck actually comes from Deep Future Analytics. I'm CEO of DFA. Many of you will know me from Prescient Models, which I founded about 10 years ago. We've actually merged DFA and Prescient. The distinction in the past was more about branding than anything else. And so the new DFA is focused on software tools for pricing optimization, CECL, stress testing, loan pool valuations, lifetime customer value, those sorts of things. We've got a software suite that implements models for you. And then on the consulting side, we do a lot of custom model development, model validation, and training. So that's the sales pitch for today. If you'd like assistance in any of those areas, please let us know. So let's start with what is machine learning. Of course, we have to start by asking that question. I didn't come up with this, but I did see once that machine learning is written in Python or R, and AI is written in PowerPoint. And I especially liked that, obviously tongue in cheek. There is most of the machine learning algorithms out there are coming out in Python, and of course, accessible from platforms like R, and I know SAS has a lot of machine learning, so machine learning is everywhere. AI is perhaps even less well-defined than machine learning, but I would say that for me personally, machine learning is about things that are nonlinear, that have interaction terms, or cases where you're using ensembles. AI, most of the time when I see scientists use the term AI, they're talking about neural networks, particularly deep learning neural networks. I don't usually see AI attached to stochastic gradient boosted trees, for example. which is probably one of the most popular machine learning algorithms. Now, on the left of the screen, I borrowed the definitions from another researcher, and I should have referenced that on here, but it's in my paper in the Journal of Credit Risk on survey of machine learning. It's interesting that the first two items here are basically to say what machine learning is not. So uncertainty, it's saying statistical models take the uncertainty into account when specifying a model for the data, whereas machine learning doesn't usually have this. And structurally, statistical models usually have an additive structure, or where there are interaction terms and other things, they tend to be linearized and made additive so that you can get overall some kind of a additive structure, thinking about things like regression, logistic regression, that sort of thing. Machine learning is, I think, more empirical. It allows for these higher order interactions. It allows for learning structure from data as opposed to coming to the problem with the structure predetermined. And I think it's fair to say that many of the things, at least in our space, that we learn from machine learning and that we do with machine learning could actually be taken back to a linear structure. There are some very famous vendors I know who use neural networks, for example, in order to identify important interaction terms or important nonlinearities. And then they take that knowledge back to their typical scoring model and drop those in. So there is a very big gray area here between what is machine learning and what is more traditional statistical models or linear methods. But I think I'll just stick with, we're going to focus on things that are nonlinear and also the ensembles aspect. I think traditionally ensembles were not a favorite in statistical modeling, but there's really no doubt that they are more robust. And I think last year, our own personal experiences showed a lot of benefits from ensembles. So I'm getting ahead of my slides here, but if I start with strengths of machine learning methods, and really in going through these slides, I have to say that I am very allergic to hype. I got my PhD working in chaos theory, and that's a term that was heavily abused by marketing buzz, where many things were called chaos that had nothing to do with the scientific definition of chaos theory. There's plenty of that going on with machine learning and AI, where things may get called that for marketing buzz, when in fact they're really not doing anything abnormal. So I know that for myself, I have been skeptical in the past, and yet there are some real success stories with machine learning as well. So I want to be as balanced as I can here. So starting this off with the positives, machine learning models are almost required for some of the unstructured data that we want to start using in our models, some of the data that is not numeric or even categorical. So when we talk about analyzing text or voice to text and chat bots and all these things, that is definitely the domain of machine learning methods. They are good at finding nonlinear relationships when you don't know what those might be. And in very high dimensional problems, especially fraud detection, it may be extremely difficult to get a low dimensional view of what the nonlinearity is. Credit scoring is usually more tractable as far as understanding what the nonlinear structures are. But in general, it's a good way to start to understand them. Many of the machine learning methods we use are also very robust to non-normal distributions. And I think it's very important as you look at these methods to understand what are the underlying assumptions that the method has about normality or not. And so, whereas some machine learning methods are robust to non-normal distributions, not all of them are. Finding interaction effects is, of course, one of the most important features of machine learning, where you've got a higher dimensional perspective on things. And as I just said a moment ago, achieving more robust forecasts through the use of ensembles is certainly proving to be beneficial. Now, in using AI through the stages of model development, I want to talk through data gathering, factor creation, model development, and validation. And I think it's important to separate these out because some of the big successes are coming in areas of data gathering and factor creation. And the European Central Bank, the ECB, put out their guidance on AI and machine learning, I should say proposed guidance. One of the points they made was that they view data gathering and factor creation as low risk, that you can use these methods with less scrutiny than you would if you're using them for final model development. And that's an important distinction, I think. So what I mean by data gathering is going to be, website scraping, processing call center logs, a lot of other alternate data sources that are very either text-based or unstructured. Factor creation is taking data like that and perhaps running a sentiment analysis. Whereas, so sentiment may not be what you're trying to predict, but that may become an input to another model. In model development, really the strength, I would say, of machine learning methods is to find pockets of predictability. That linear methods are trying to find predictability everywhere, but I think sometimes there'll be problems where you have less predictability in certain cases, but in a higher dimensional space, you can find a pocket with clear predictability. So the pockets of predictability are powerful, but they also come with risks that we'll discuss. And then I have some comments on how to validate and monitor AI and machine learning models based on our own experiences. We've started doing a lot of this kind of work. And I think we all know it's important to discuss how one validates and monitors these things, but I think it's important to know at an intuitive level where the weaknesses are. Even if a model passes validation, we haven't seen them through a lot of economic cycles, obviously. So we need this intuitive understanding of when they might fail, even if they haven't before. Okay, so a few comments on data gathering. This won't be the heart of my talk, but the promise is to look at things like voice to text. I was looking at new methods for image captioning. So being able to take image or video to text that can be analyzed. I've seen cases of ID verification. Is the picture on screen and the ID the same person? So there's always been a lot of application in fraud and anti-money laundering, those areas. Credit risk is a little different in this regard. Some of the challenges that we face is changing data formats and definitions. And we've seen this through the pandemic, that some data fields no longer meant exactly what they used to mean. Either the data couldn't be gathered the same way. This was obviously true in a lot of economic data, but it can be true of the consumer data that you're used to gathering. We also have this issue of very limited history, and this will impact what we can use machine learning for today. And I'll come back to that, but having short history and continuity risks is an important issue. That are we certain that some of these novel data sets will be available in the future, or will, as I said, mean what they mean the same thing in the future? Now, There is open banking, of course, which has already started to have an effect in Europe. It really hasn't taken off yet in the US, but at least on the side of financial data, this could be an interesting impact. In fact, maybe this shouldn't have been under challenges, but it's more of an opportunity for standardizing data. But just generally, data standardization is an area where machine learning can help, but it's also a risk that we don't have much experience and these things may change. And so I wanted to show you this example. I found this week. Of course, I've seen this data before, but just wanted to see an update. On the left, what you've got is a graph of consumer mobility from iPhones, essentially, Apple's mobility data. And we're looking at 4 countries, US, UK, Italy, Germany. That just happens to be the example that came up. And you can see how mobility drops with each COVID wave that happens. Things had largely recovered through the middle of this year, but now you can see them dropping again. And there's a clear weekly oscillation here, so it makes it easy to count off. The last 4 or 5 weeks, mobility has dropped significantly. This is probably in response to the Delta variant surge that we're having this winter. It also, we will want to track things like this to see in coming months what impact Omicron might have. We don't know yet, but really it's a question of how consumer behavior will be affected by that. It's, you know, everything through the pandemic has been more about the fear and uncertainty and, you know, changes in behavior. In fact, on the right is an interesting view of mobility split between driving, walking, and public transit. This is an example for the Chicago metro area. What you can see through the pandemic, kind of from April last year up through around May and June of this year, is that walking and driving were right on top of each other. You know, what does that mean? In the Chicago area, if you're commuting to work, you probably have to do both walk and drive. Whether it's a big parking lot downtown or in working in a large corporation. So clearly people were in their vehicles more. And so you saw this correlation of driving and walking, much less public transit. And then this year, especially starting in early summer, you saw a separation between walking and driving because now people might be walking to public transit or from public transit, and the amount of public transit was returning to normal levels. But in the last few weeks, you see it reverting back to previous patterns. Now driving and walking are aligned and public transit is declining. So it's a fascinating pattern. Data like this could tell you a lot about how consumers are behaving. I wouldn't say this is necessarily something you'll use in your credit risk models, but it does give you an idea for different metropolitan areas, what's happening with the pandemic and what impact that might have on employment and income and such. But the question, if you were to actually use this kind of data in any model, how long will it be available? There was a data set last year that I was tracking pretty closely from a company called Womply that was publishing weekly credit card transaction data at merchants. And so it was a way to see how many merchants were open, how it was affecting different industries. Really great data set. It's now gone. I guess they decided it was for purchase only. So after about 18 months of making that freely available, that data set's gone. A lot of new data is coming out, but we have no certainty how long it'll stay available. Google has already decided that their mobility data, you can only see the previous 4 weeks. And so if you pull up the Google chart and look at just the last 4 weeks, you can't tell much more than flat. In fact, it might only be 3 weeks. So there's very little valuable, useful information in that as compared to these long-term trends we see here. Nobody knows what Apple will do in the future. So these alternate data sets are fascinating, but it's hard to build models on them when you don't know how they're being gathered. You don't know the reliability of or the accessibility of them in the future. So just something to consider. And I guess I bring that up because alternate data and machine learning kind of go hand in hand. Many of the alternate data sets that we talk about, you need machine learning methods to turn them into factors. And that's the next section here. So some of the interesting kinds of alternate data we've been seeing, cash flow analysis, scrapers of deposit and checking accounts to understand consumer level cash flows has been very valuable. Some folks are using convolutional neural nets. Now, convolutional neural nets are usually used for image processing, but I've read papers on how they've been applied to credit card transactions to extract factors, basically to find common patterns among credit card transactions so that you can group different kinds of consumers. Then, of course, we mentioned you can do sentiment analysis on call center logs, chatbots. You can analyze what's going on in the chatbot. And this is all using natural language processing. And then there are IT uses, IT data rather. So what operating system is somebody using when they connect to mobile banking? What time of day did they connect? IP addresses, things like that. Now, any of this you could use in fraud prevention. But if you're going to be using data in account underwriting, new loan origination, you've got to be very careful. Clearly, cash flow analysis, you could. The last one on IT data, there have been papers by folks employed at regulatory agencies saying that these things highly correlate to protected class status. So there are a lot of regulatory and reputational risks with using some of these other categories. But things that are basically financial information, of course, is fair. A comment here, which is interesting, that convolutional neural nets are a key part of Zillow's Z estimate. I didn't know that. That's fascinating. I think the Zillow estimates are interesting. Of course, there was news recently that Zillow shut down their home buying program, and there seemed to be some concern about the machine learning methods they were using to predict which houses were good to purchase and flip. They had basically a home flipping service that they shut down. They've taken quite a loss for it. It's unclear to me if the algorithms didn't work or if they weren't used properly and perhaps weren't used over the right time horizon. It may be that the models work in average over long horizons, but going in deep all at once was probably a bad business call. So hard to know from what I've read, but that is not the best. Their Z estimates may be fine, but their use of them is a cautionary tale of how you have to ease into using some of these machine learning methods. It's not unlike going into lending in a new credit tier. I've heard people say, yes, they know there's yield opportunity in the higher risk segments, but they want to do that very cautiously, do a lot of testing and so forth. If you would do that with lending, why wouldn't you take that approach with some of these modeling techniques just the same? Yeah, another comment, also unclear about whether Zillow was overriding the model in outputs. I agree. It's hard to know. So I'm not willing to damn the model at this point. It's pretty clear there was some questionable business decisions, but I'll leave it there. Now I'm sure Many of you have seen xkcd.com, which is kind of comics for nerds. This I thought was a perfect representation of our lives going forward. Every data table from now on, you're going to have a star and a dagger by 2020 and 2021. This data is weird. And that's a very interesting point when you think about machine learning, because as I mentioned, machine learning is all about finding nonlinear patterns. And usually a nonlinear pattern is not universally nonlinear. It's more like saying a pocket of predictability. There's a certain behavioral pattern you can find that when you see this, you know something about that consumer, which gives you an opportunity to make a certain offer, that they may be interested in a certain loan, that you know that their potential yield is good because their risk of default is low, or whatever the combination is. Those behavioral patterns that machine learning is ideal for finding are the things that are most susceptible to change when the environment changes. And so when we looked at data from 2020 and 2021, machine learning models are more likely to break in the face of a sudden change like that than linear models. And I should say linear models on traditional inputs like financial data from credit bureaus. The bureau scores didn't do too badly. And it's because they're, models that have been built on very standardized, very linearized data for a lot of years. There are no pockets of predictability in bureau data. It's all been so linearized that it's pretty straightforward, and those models are more robust through the crisis, as long as you can still gather the data reliably. Not so much so with machine learning models, and I have heard this concern that the machine learning models were prone to failure, certainly in the beginning of the pandemic. And so what do you do if your model is at risk of failure? It means you need a fallback. And so this gets to some of my recommendations later, but when you talk about a fallback, we do need to keep in mind that with these data sources and models being new, we are going to need some kind of a benchmark or a fallback model that is a little more well-known and a little more reliable, even if in normal times it might have less discrimination ability. Now, I think what's interesting, will the new normal of late 2021 and 2022? So have we reached the new normal yet? Actually borrowed that text from a slide from early in the year, and perhaps not. Perhaps we are still waiting for normal, especially with Delta and Omicron. But I think there's a good question of what data do we train on? Are we going to be looking at data up through 2019, skip over 18 months, and then start training again? What's the best model to use today? Is it the 2019 model, or one that brings in data from the last 18 months? I'll tell you, my personal bias or personal intuition is that we're more likely to head back towards 2019, at least as, assuming things settle out in early 2022. It seems like the best approximation might be 2019. Certainly what happened in 2020 and early 2021 is not normal. Default rates were way below what they should be. Behavior was certainly abnormal. I think the future will be different. People's behaviors will be fundamentally changed going forward. Work at home people are not the same as what they used to be. There are a lot of other things, if you looked at whether somebody commutes to work or not, that certainly doesn't mean today what it used to be. So changes will occur, but we'll have to contend with that. So when a structural break occurs, like we had early last year, there's going to be a lag before you know what the new pattern is. And I'm not new to machine learning. I'm new to the name machine learning, because when I did my thesis in chaos theory, and I realize now I count the time back to that in terms of decades and not years, all of the methods I used were what we now consider machine learning. I was working with genetic algorithms, and pockets of predictability is a phrase I am borrowing from the thesis of one of my uh, co-workers in the lab that I was in. And so we've been working with these methods a long time, but not in banking. Now that we're trying to use them in banking, some of the old lessons we had, things about it takes time for a new pattern to form. So if you wanted to use the new normal as what you're going to train models on, well, let's say that we establish the new normal in 2022, then it takes 6 months to a year to start to get outcomes that you can model against. And so it may be well into 2023 before we can actually train up machine learning models that find those high value pockets of predictability from the end of this year and next year. So that's why I talk about having a backup model. And comment here on LIBOR, talking about things that change in terms of data. Of course, we know that the scandal with LIBOR interest rates and the forced changes that are going to happen, and that's a series that's going away eventually. There's a little bit of a window there, but it's yeah, sometimes you have no choice but to move forward. I understand. Now, as I've been looking into what is deep learning really doing, what are some of the machine learning models really doing for you, the image that I've settled on is that we've been doing things like principal component analysis for a long time. My first job after my thesis, we made heavy use of singular value decomposition, essentially a kind of PCA. And the idea was to take a huge number of inputs and distill them down to a key number of factors. And when we look at economic data to describe what's going on in the economy, we may be looking at hundreds, as much as 1,000 different factors and lagged values of those factors. If you distill those down through a principal component analysis, you tend to find 15 to 20 actual factors before you get down to just nothing but noise. So I think one of the best ways to think about the early stages of a multi-layer artificial neural network is that they're doing a nonlinear equivalent to principal component analysis. They're trying to get to concepts. And there was a lecture given by a researcher in language translation. And what they had done was to create an algorithm that went many to many languages through a single neural network out to many languages. And it was an hourglass shape. You often see these hourglass shapes when you have to predict many things and you're taking many kinds of inputs. The reason there's a pinch in the middle is that that's the concept layer. And that was the phrase that this other researcher had used. And so the idea is to take the many inputs you may have down to what you could call key concepts, and then use those as inputs to any kind of modeling you want to do. And I think this idea of a concept layer is really where AI is headed. That when you talk about true artificial intelligence, artificial general intelligence, what's it going to take to start to approach the intelligence of animals and eventually humans? It's all about going from raw inputs through concept layers and then starting to manipulate concepts. I believe that's what humans do. And so by going through these concept layers, the goal is to avoid sensitivity to single anomalies. And also it makes things more explainable. Now, I should mention that many people in our field like very short networks, only a couple of layers, but perhaps very wide because you've got a lot of inputs. That makes for good explainability. You can see 2 or 3 factors going into a node, which you can actually interpret specifically. This is the concept that node is creating. So I think it's good to think about it this way. Even though I'm using a neural network image here, you can still have that sense of concepts when you're looking at a tree, because there it's specifically trying to find pockets which have certain boundaries to it when looked at as kind of a hypercube that is defining a group, defining a segmentation that often is interpretable. Now, there's a comment here I'm going to have to read out loud so that I can follow through. Because of the problem of structural breaks in economic behavior and change in the meaning of data elements, Leonard Roseman, hi Leonard, always looks to see if the modeler has built-in good monitoring to detect changes quickly. Having a backup model to compare against would be a good approach. I absolutely agree. And when we talk about model monitoring, there's not nearly enough monitoring on model inputs for stability. And also, when those inputs are turned into factors, making sure that the factors can't blow up. We saw linear models break dramatically, or let's say logistic regression models is in my category of linear. They broke dramatically last year just because the inputs had rates of change that they had considered impossible, and the models started generating infinities. So we've got to be a lot more careful about those kinds of things. You don't want to get to an operational failure because these anomalies were not foreseen. And that's why we like certain kinds of transformations on the inputs. And there's no guarantee that a machine learning algorithm will learn the same kind of transformation we might impose. For example, I like using log odds because then you can't blow up. I like using log ratio over 2 periods of time instead of percentage change, because again, things are normalized, kind of linearized. One of the risks with machine learning models is that they only know the data they trained on and they don't have this bigger vision. I think as analysts, we need to be not afraid to try to encode our own prior knowledge into the structure of the machine learning algorithm, because these algorithms only have a few years of knowledge, and we and those who came before us in their books and papers know a whole lot more about long run patterns than the algorithm will. It's really important to include that. So as far as model development, when I wrote my paper, Journal of Credit Risk asked me to write this survey paper. I had no idea how massive an undertaking it would be. I had 400 references just in the area of credit risk, almost only in the area of credit risk. And it's quite popular to basically pick one from each of these columns, mix them together, and give it a new name and publish a paper on this algorithm. I have to say I'm not a fan of that. It's the goal is to understand what the strengths and weaknesses are across here and to mix and match according to your problem. And no specific combination of these things is going to work in every case. But just to read this slide, on the left, we have architecture. So additive effects, that's basically a linear model. Additive fixed effects, that's having non-parametric inputs, factor inputs. Convolutional networks, like we talked about for image processing, clustering, fuzzy rules, nearest neighbors, recurrent neural networks, state transitions, trees, all these things are really an architecture. Now, they all have parameters. How do you optimize those parameters? If you're statistically minded, you can use an estimator. And there are ways to use statistical estimators with many of the structures that we think of as being machine learning. On the other hand, many people will define machine learning as being the use of non-statistical optimizers. I would say that's not necessary, but if you did, gradient descent, backpropagation in neural nets, genetic algorithms, Markov chain Monte Carlo, linear programming, all these things are, again, other ways of setting these parameters. Which combinations are best? I absolutely believe there is no universal answer. I will say ensembles are almost always a good idea. I want to highlight that in green. We can argue about whether you want to use a neural network or trees or something else, whether you want various other things. But when it comes to optimizers, you almost never want genetic algorithms. And this was a big part of my PhD thesis back when. If there's one method on this page I know a lot about, it's genetic algorithms. And I almost never use them because you need a very specific symmetry in your search space for them to work, for things like crossover to be a useful method. You also, to make them effective, to make them not just massively computationally expensive, you have to do a lot of work and make sure you really understand your space. So I'm always skeptical of these unless there's a certain symmetry in the meta parameters that you're looking at or something. But aside from that, the rest is going to be tagging them to the right architecture to focus on the problem. Now, I went through, this is purely heuristic. I looked at a number of different criteria that one might consider. On the left, I was thinking from a credit scoring perspective. On the right, I was thinking from a time series modeling perspective. And I just chose a few methods. So something like K nearest neighbors. K nearest neighbors is just, treat your data as a database where, given a new account, you go look up the ones nearest to that one and take some kind of average. There's not a whole lot of a model there, but if you have very low data, you may not be able to find much pattern other than just find the ones nearest to that. So I give that kind of method good marks on low data volume. Other methods, when the inputs are very nonlinear, that's where you might like the decision trees, and especially stochastic gradient boosted trees are a special kind of ensemble. I meant to mention on the previous slide, there are many kinds of ensembles, but ensembles of trees are great with nonlinear inputs and with non-normal distributions. So lots of things to consider here, like how many extreme outliers do you have? And can you identify them? Can you predict that you'll have to deal with them? That can affect which methods you'd want to use. If I'm thinking about things on the right, I would swap in recurrent neural networks, are a time series method people use. There are a number of things to consider. Few cycles is a key consideration. In our industry, a cycle, I mean an economic cycle, and we almost never have enough economic cycles for the kind of modeling we want to use. In fact, I always say, if you go pull out a time series book written by a statistics professor, the graphs, the examples in there will always be back to 1960, 1940, 1920. They've got many economic cycles in their examples where we often have one or even less than one. And so that's where you need very robust methods like ensembles. That's where you need to look at things that are easy to add your interpretation to. Actually, a lot of times regression methods give you that interpretability, which are very valuable in our space. So machine learning has challenges if you wanted to use it for time series modeling in our space, even though things like recurrent neural networks are a huge win when you're looking at speech recognition and a lot of high frequency time series data that's being modeled. So our situation is different. Something that I'm also very concerned about is what I call p-value arbitrage. Um, I'll start by saying that I think we often have the wrong, or at least had, I think this is improving, but if I go back 10 years, model validation was heavily focused on p-values in our industry, and still does look at that a lot, but at least the interpretations are improving. But a significant p-value could mean that, if I had three different factors, this graph on the left is meant to say, let's imagine we've got three factors. One of them I have very low sensitivity to, but my confidence in that low sensitivity is very high. That one is the one most likely to be retained if I'm filtering on p-value. Machine learning models generally don't compute p-values. And so if I have high sensitivity to something, but with high uncertainty, without a doubt, that's what the machine learning algorithm is going to zoom in on. And so we don't want to be using machine learning algorithms simply because we prevented our linear models from using the same factors. So this idea of model arbitrage, just because of how we validate, I think is a real concern that we need to think about. How do we standardize the assessment of models across all model types and not just wind up choosing certain ones because of how we tend to choose to review them? I like Leonard's comment here about he's always found support vector machines and Bayesian model averaging to be theoretically beautiful, and I agree. There's some fascinating things, especially when you look at using certain kernels in support vector machines, so that you are changing kind of the dimensionality of your space and things become separable where they weren't before. There's some really cool stuff there. And yet I also haven't seen them used a lot successfully in credit risk. And I think part of it, especially in credit risk, well, I'll get to this. I'll try to make sure I come back to another point of validation, but let me get through this. I've already mentioned that behavioral shifts are a key concern. And this idea of transient structure is something that we really have to be worried about with algorithms that are able to find it. My first job after getting my thesis was using machine learning algorithms to make forecasting models for currency futures. The biggest problem we had was not finding predictability. There are pockets of predictability all across that data, no matter where you look. But as soon as traders find it, then they trade it out and the pattern disappears. So the problem is you'd look at historic data and it's full of structure. You build your model on that structure and then you go to use it out of sample. And almost as soon as you find the structure, it disappears. And then what you need is a way to filter out the structure you know is there to look for the more subtle structure underneath. And that is a very real world example of the challenge that machine learning models have, which is we often think that they're adaptive and they keep up with the patterns and the structure, but in our industry, it can take 2 years to know what the outcome of a test was. That's a long time to wait. And so this adaptability of machine learning models isn't actually able to live up to that promise because of the slow time to see the outcome. So transient structure becomes a real problem. I think another thing that is not recognized enough is that in a linear world, this is not actually true, but I'm going to say, I think there's a general assumption that the uncertainties are more or less uniform across the range that we use the models. And I would say there's an assumption of that because people ignore the uncertainty. If you look at model implementation and people implement scores, I have never seen a score implemented that also came with an uncertainty, and the uncertainty being unique to the individual, where you are in the space of the model. It will, of course, become more uncertain as you get towards the extremes of the model. But kind of in a in a gradually predictable way. And so I think we tend to live in a world where we hopefully ignore that non-uniformity of the uncertainty. With machine learning models, that is not at all true. A pocket of predictability can occur anywhere, and each of these pockets is going to have a different uncertainty. And if you're between high confidence pockets, your uncertainty may be very high, even though you're not particularly extreme. And so with nonlinear models, we have to do a much better job of understanding the uncertainty around the forecast. And I think especially with, well, when I say nonlinear, if the rate of change is high, it means the change in uncertainty can be high. With trees, as you cross boundaries from one node to another, one leaf to another, you can get dramatic changes in uncertainty. So this is something where to use these models confidently, we need to do a lot more work on understanding local uncertainty. Now, one point that this is just a preview of a topic we're going to give an entire talk on. Jeannie Leonova is going to talk about work we've done around, there's this assumption that AI and machine learning methods have big data, but we really only have a couple years of big data, or at most, the best I've heard is 3, 4, 5 years of big data. But our economic cycles and our product life cycles are very long. And so the small slice that we have of big data isn't able to show us how the models might have performed in other epochs. And this is where right now, the structure we see looks like it's transient, like it's rapidly changing. And that's because we have no concept of what it might have been like in previous periods. And we're not going to for a long time because we have to gather this data. So what we have done is to find a way to combine vintage modeling, age period cohort models, with stochastic gradient boosted trees or with neural networks, so that the machine learning models, with their short history but a very rich data sets, can find all these pockets of predictability, but do it in a way that is centered around the long run structure that we can get from these other models. So basically, we want to combine what we can model from long, thin data sets with what we can get from machine learning on short, rich data sets. So this is some of our newest work, and I encourage you to join that talk in about a month, because I think it'll be very interesting. And that's actually what this is a visual about, how we can combine life cycle and environmental measures as parts of a neural network or a machine learning algorithm, basically using them as fixed inputs. So we'll come back to how this can work in that other talk, but just as a preview that I think that's pretty promising as a way to leverage what we know from decades of long-term modeling with what we know from some of these newer data sets. Now, I want to use my last few minutes here to talk about model validation. And this comes from our experiences. Validating machine learning models, of course, is an interesting area. And because we have, I'd say we're fortunate that we have backgrounds in machine learning, and that has become popular in credit risk. So we have this opportunity to use what we've learned from years past in this new application area and what the strengths and weaknesses might be. What we have found as we look at these models, first of all, is checking the meta parameters and the assumptions. And this is critical. I and my team have done model validation where the first thing we do is look at what are the distributions? What are the assumptions in the algorithm you're using? Does it need the data to be normalized? Does it say that it works best if the data is between 0 and 1? things like that. Um, Too often we see the data just dropped into a canned algorithm on the assumption that the algorithm will figure it out. And that's not always the case, of course. I'm also starting to see cases where people have built machine learning models that they're very proud of, but they never actually built a linear model. So they don't know if the machine learning model is any better than what it could have been otherwise. And especially if what you're doing is taking inputs from things like bureau scores and somebody's fraud score. And, you know, when something has been distilled down to a score, almost all the scores I know of are built so that they're linear in log odds, that as you look at change in FICO, you get a linear response to change in log odds. At that point, you don't really need to feed that into a nonlinear algorithm unless you're combining it with some other unusual data. In fact, I've seen cases where all of the inputs were essentially scores. All they really needed was a principal component analysis to pull out the primary factors and create a linear model. So this is where hype gets ahead of necessity. And I think we need to view it as a necessity to compare any machine learning model to a roughly equivalent linear method, just to say, have you done anything worthwhile? Because machine learning models do carry risks of robustness out of sample and a number of things that we have more familiarity with how to control in linear methods. As I mentioned before, I think it's a matter of policy, but I think I strongly recommend parallel runs with linear methods. As one comment said, this is useful for tracking model failures. Now, either model could fail. If the linear model flew off as compared to the machine learning model, you'd want to know why. But if you're going to have a benchmark, and if one of your models is a machine learning model, definitely go with something linear as a benchmark so that you've got an understandable point of comparison. And then the last point on here, we'll have a separate talk again on ethical bias. There's no way to overemphasize the issues with ethical bias. Unintended bias is huge as a problem because we're not allowed to collect the data. We don't know. For example, the Apple Card, Goldman Sachs, they built their model and someone claimed that there was bias against women in the terms offered on that card. The response was our developers didn't use that factor of whether somebody, men or women or ethnicity or any other protected class. If what they used was machine learning, that is not a good enough argument. You are not protected from bias just because you didn't use protected class status in your model. In a linear context, you largely are protected, but in a nonlinear context, you can infer these things, unfortunately, quite easily. So we'll talk more about this, some ways to deal with it, but it's going to be a hard problem until we can start gathering that information. So that's what I had to say. Thank you for your time. I understand if people need to leave, but also I'm happy to stay on and answer any more questions. And I've appreciated the comments that have come through as I've been talking.